No, see, not lined up right all of a sudden. Okay, so the parent function for the greatest integer function kind of looks like the absolute value. So it's still y equals, and then instead of, it's just going to have x. That's what all the parent functions have, and then whatever the kind of function does to it. So for absolute value, it was x, and the x was in absolute value bars. For the greatest integer function, it's still x, but the x is in these bracket-looking things. Okay? So these brackets have a specific meaning. They round the number inside the brackets to the greatest integer it can be without passing up the number that's inside of the bracket. So that's a little bit weird. Okay, so what it means is if I have this, see how it's like not lined up? And let's say it said like 3.6 inside of it. So 3.6 is not an integer, it's a decimal. Integers are whole numbers, 0, positive, or negative, okay? So 3.6 is between which two whole numbers? 3 and 4. So one of those is what you get with the greatest integer function. Now it's called greatest integer, so people automatically always want to round up. But this is round to the greatest integer without passing the number that's in the brackets. So if you have to round it to either 3 or 4, but you cannot pass the actual number that's written up there, 3.6, what are you going to round it to? 3. Okay? So this gets rounded to 3. What other numbers, if they were inside the greatest integer brackets, would get turned into 3 also? 3.9 would still get turned into 3. What else? 3.2. 3 point anything is just going to be 3 because it can't pass it. Okay? When could you start getting 4? Yeah, if 4 was in there, it gets rounded to 4. It can be itself, okay, because it hasn't passed itself. And then you have the 4 point something, 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 somethings would all get rounded to 4 until you reached 5. And then those things would get rounded to 5, okay? So it gets a little bit weird with negatives, too. If negative 2.4 is in the bracket, what does that become? Not positive 2, so it doesn't, negative 2, so do we agree? Okay, so I want you guys to think number line. It's hard. Okay, number line. If this is 0, negative 2.4 is somewhere over here. What are the two numbers that negative 2.4 is in between on the number line? Yeah, negative 2 and negative 3. If I have to pick an integer to round it to, but I cannot be greater than negative 2.4, it actually is negative 3, because remember how negative numbers work. Negative 2 is actually bigger than negative 2.4. That's why it doesn't get rounded to negative 2. Super weird kind of with the negative numbers, right? So this is going to become negative 3. Okay? So it makes a very weird graph, and I know I'm trying to record it, but I can't draw it up here accurately because nothing is lining up right. It's slightly off. So I'm just going to draw it with this. So basically on your graph, you can make an x and y axis if you don't already have them on there. And if we assume that these are numbered by ones, okay, think about if you just plugged stuff in. So if I plug in 0, what am I going to get? 0. When I plug in 1, what am I going to get? 1. When I plug in 2, 2. So everything that's already an integer is just going to stay itself. So when I plug in negative 1, I get negative 1. Negative 2, negative 2, negative 3, negative 3, etc. But do I connect them with a line? Okay. So no, because when I plug in 0.5, it's not like it goes up to some point in between 0 and 1. When I plug in 0.5, what does it get rounded to? So 0.5. It gets rounded to 0. So it's still at 0. Okay. What about 0.2? Still 0, right? What about 0.9999? 0, okay. Until I get to what? 1. Do we know what the number is right before 1? It's like a really weird math question. Because you want to say yes, but like really do we know? No, because someone could just keep adding 9s in between here. So all I know is that it's going to keep getting rounded to 0 all the way up to 1, and then all of a sudden when it becomes 1, it's going to make this jump up and be 1 now, and that's going to be it. So the way that looks on the graph is that all of these numbers still stay at 0. Okay, 0 is the y-coordinate that goes with them, all the way up until 1. So I'm going to put an open circle at 1, 0, because I don't know what number comes right before it. So I can't stop it anywhere else. I have to put the symbol that means go all the way up to this. But then when you finally get there, do you have a point at 0 anymore? No. When you plug in 1, you get this point up at 1. Okay? Then what happens when I plug in numbers that are between 1 and 2? So 1 point somethings. What do they all get rounded to? 1. Okay? Anything that's, if I changed all these to 1s here, they would all get rounded to 1. So all the numbers that I plug in along here all get rounded to 1, so that all their points would be along here, until I reach what? 2. All the way up to 2. Do I know what number comes right before 2? No. So I put the open circle at 2, saying, you know what, all these guys get rounded to 1, and then right when I get to 2, I make the jump up to 2. So do you see the pattern of what's happening here? Okay. So it's making these little bars. And these bars continue in this pattern forever along the graph, but you don't have to fill up the whole thing as long as you understand that. And so we would see them like this. Okay? So plugging in points in this problem gets a little difficult. I'd rather just know some rules for kind of switching the parent if they plug in some numbers. Because all of a sudden now if they plug in numbers, I have to add, subtract, or multiply before I do the rounding. Then I might have to add, subtract, and multiply after I do the rounding. It could get really complicated. Okay? So we'll talk about what those changes are in a minute. We'll look at a couple of different graphs that we could see the difference between. So for the verbal description of the graph, write down anything you can see. You can talk about steps. You can make sure that you notice that one of the endpoints is closed and one is open. Some other important pieces of information. How long are the steps? 1 unit long. And how far apart is each step? 1 unit apart. Okay, so that could help you quickly create this graph if you knew those pieces of information. So things that which end has the open point, which end has the closed point, that they're 1 unit long and 1 unit apart. Okay. Is there any objections if I change it to the next screen where we can fill in the domain and range and stuff? You don't have to do the box without explaining why it works for right now. Okay, so domain, range, x-intercepts, y-intercepts. Graph is still here, that's convenient. Okay, so domain. What's the domain of this function? What were we allowed to plug in? All real numbers, right? I can plug in any x value along the graph, and there is some y value that goes with it. So the domain is still all real numbers. The range is kind of weird. So is there a maximum or a minimum? No. But do you hit every number? No. There's like some big jumps in between, right? Like I'm all at 0, then I'm all at 1, then I'm all at 2. Good. And integers covers positive and negative. So if we just say integers in this case, it's covered. Okay? So the range here are all integers. There is a notation for that too. Yeah, sorry. It's just like weird capital bold Z thing. All right, x-intercepts and y-intercepts of this function. So what are our x-intercepts? So definitely at 0, 0, but there's actually a lot of x-intercepts, right? Like every number between 0 and 1, there's really like infinitely many. Okay? So for here, you don't have to list them all. That would be impossible. And for right now, I would be okay if you guys could just say that there are many of them. Okay, like infinitely many of them. And again, that's because all of these points were along the x-axis. What about the y-intercepts? So we get the y values of 1, 2, 3. That's the range. That's the integers. But where does our graph cross the y-axis? At 0. And I know you see a point on the y-axis here at 1, but it's open. So is it really hitting the y-axis at 1? No, we're trying to say, like, go all the way up to this and then, like, and then you jump, right? So the only real point on the y-axis is at 0. So the y-intercept is just the 0, 0 point. All right, for the slope, rather than call it slope, okay, again, I'd want you guys to point out how long the steps are and how far apart they are. And the reason I'm saying to point that out is that will help you when we graph it in the future, because we'll change that based on where certain numbers show up in the equation. So I would just say that the steps are 1 unit long and 1 unit apart vertically. So I know kind of a weird graph, but it also demonstrates some things for us that will help us kind of generalize these transformation rules that we want to use. Okay? So the next part you guys don't have to write down. We're not going to go through the graphs on the back of this until maybe tomorrow. It'll just depend on how much we get through today. So your goal today is just kind of try and absorb what's happening when numbers show up in certain places in this equation. So we're going to look at 2 graphs. Okay. Both of them have just inserted a number 2 that's multiplying the function, but the difference is that the 2 here is multiplying inside the greatest integer function, whereas the 2 over here is multiplying outside of the greatest integer function. And our goal is just to look at what happens when we do this. Okay? Once we see it once, we're not going to plug in points anymore to determine what happens when we do this. Instead, we're going to kind of make a rule for ourselves that's just going to let us see the number and know automatically what to do to the graph to make our life a little bit easier. Okay? So first, though, first time looking at it, let's think about what happens when we plug in certain numbers. Okay? So let's say I plug in 0, first function up here. So you'd put 0 in. You'd multiply 2 times 0, so it would still be 0, and then you'd do the rounding. Okay, so it's just going to get rounded to 0. Okay, and then what happens when we plug in 1? What are we going to get? 2. And then when we plug in 2, 4. That at first doesn't appear much different from the other function. Okay. When we plug in 0 here, 0 would remain 0 even after the rounding stuff, and that times 2 would still be 0. When you plug in 1, because the integer function, when it's already an integer, doesn't have to round it, it stays 1, and 2 times 1 would be 2. And when we plug in 2, we would end up getting 4. So at first, they don't look very different. Some of their points would look exactly the same. So you can go ahead and put those on the graph. Yeah, see, this is going to work really well. So go ahead and put, well, you guys aren't graphing it, so we'll put them up here. So we have 0, 0. We have 1, 2. And then we have 2, 4. And these points exist on both of the graphs. Okay. So then the question is, what's happening in between? Because there's got to be something a little bit different that's going on. So I'm going to pick numbers in between 0 and 1 and then try to see what's happening to the graph. Okay? So let's say I plug in 1/2. Okay? So in this first function, when you plug in 1/2, the first thing you would do is you'd multiply 1/2 by 2. 1/2 times 2 would give us what? 1. And then that, when it gets rounded, will stay at 1. Okay? So in this function, when I plug in 1/2, I get 1. So at 1/2, I have this point at 1. when I plug in 1.5 or 1.5, okay, 1.5 times 2 would be 3. Then when I round that, it's just going to stay 3. So I get 3 in here. So at 1.5, I'm getting 3. Okay. All right, so you kind of see the progression here. So something's going on with our steps because there's a lot more endpoints than what we saw before. Okay. Over here, if we plug stuff in the middle, what happens when we plug 1/2 in this second function? Okay, so the 1/2 gets rounded before it gets multiplied. So 1/2 gets rounded to 0 with the way this function works, and 0 times 2 is going to be 0. So this one stays along that line. It doesn't jump up a step. Okay? And then when we plug in 1.5, okay, when 1.5 goes in there, what's it going to get rounded to? 1. And then 1 times 2 will be 2. So it's staying along that line. Okay? So there is something different about these functions. Now, this one I feel like I'm starting to see the pattern of what's going to happen because I can tell the points next to this kind of still stay along this line. This one is more confusing to me because the points are still all different. So you could even go a step further and plug something in between. Like what happens when I plug in 1/4? Okay? So what is 1/4 times 2? 1/2. And what does 1/2 get rounded to? No. 0. Okay, remember it can't pass up itself. So at 1/4 I would still be at 0. Okay? So what's happening in this graph, it's going, sorry, these are supposed to be open endpoints, but I can't make it any thinner. But so it would be open here, and then it's jumping up to here, okay? And then at that point, try to make it open so you can see it. Okay? It would be open here, and it would jump up here, okay? So what's changing about this function? Are the steps still vertically 1 unit apart? Yeah, right? Still 1 unit apart, each step will be? So what's different about this function than our original parent graph? Steps are shorter. Do you guys see what James is saying? Okay? That instead of being a whole unit long, the steps are only half a unit along, but then they still go up. So the number inside of the brackets is changing the horizontal part of the graph. We would actually call this a horizontal compression because it's like it took your whole graph before. It didn't stretch it or do anything to the vertical distances, but it like took the whole graph, and it's like you take the left and right side and kind of like accordion them just closer together so that all the steps get squished to only be half a unit long instead of a whole unit long. Okay? All right, so what about what's happening over here if it's not making that jump? So these are staying along here and then hitting an open endpoint here and then jumping up. And then they're staying along there, hitting an open endpoint, and then jumping up. So what's happening in this graph? Are the steps still vertically 1 unit apart? No. Now vertically they're 2 units apart. Okay. Are they still 1 unit long horizontally? Yes. So in this graph, they didn't do anything to it horizontally. That stayed. But vertically what they did is they kind of stretched it out so that the distance between the steps changed. Okay? So how this has meaning to us. Numbers inside of the function cause our graph to horizontally either be compressed or stretched depending on what the number is. And when something's horizontally stretched or compressed, that means some horizontal distance between points is changing. Okay? That's why the steps are half a unit long instead of a whole unit long. When the number's outside of the brackets, it's vertically getting stretched or compressed, so that means some vertical distance between the points is changing. They're either getting closer or apart. Okay? All right, so you guys have a little, I think yellow, your guys' is this? The yellow paper that I had you guys like cut, but we didn't write anything on? That depends. Yeah, so this is on the back. So on the back, we're going to list all the transformations in general. There's 3 categories. There'll be plenty of room. If you write a decent size, if you write really big, you might run out of room. So what does it mean to translate something? That's like the fancy math word for something we could say an easier way. What's that? Okay, so it's not to flip it. Do you know what we call a flipping of something? A reflection. So that'll be our reflection. Okay. So, yeah. Yeah, like kind of like dragging it. Okay? Like dragging and dropping on your computer somewhere else. So it's all left, right, up, down movements, and some combination of those can get the shape wherever you want on the graph. But it doesn't change the shape by stretching it or compressing it or flipping it. It keeps the shape intact. It just kind of moves it to a different location. Okay? So translations, in case you're going to forget what that word means, this is like shifting. Okay? That can be left, right, up, down. So our translations come in two forms. There are vertical and horizontal translations. So it's on the back of your organizer. Just start at the top like it's a sheet of paper, and we'll work our way down. So there's vertical translations and horizontal translations. So think about your absolute value function. Okay? You don't have to write this part down, but just remember this formula. We did the little investigation on the calculator. Okay? Which number moved the graph left and right? The A, the H, or the K? The H, right? So basically, there had to be something added or subtracted to x, which was inside the absolute value bars for it to move left and right. Okay? So horizontal translations happen when something is added or subtracted, what we're going to call inside the function. Meaning the adding or subtracting is happening to the x inside of whatever it is that you're working with. So like inside the absolute value, inside of the greatest integer function. So like in the brackets, in the bars, in the parentheses being squared, inside with the x. Okay? So how we note that officially mathematically, you know how you guys call functions like f of x, like how we did on the last test, a lot of like find f of 3, find f of x plus h. When we want to show that something's changing on the inside, we show it like this. So this is how you'll see like the official notation. This means we added or subtracted something to x, and the x was inside maybe absolute value bars or brackets or something being squared, whatever it was that was going on. Okay? An example of that, if we were using absolute value, okay, y equals the absolute value of x plus 3. And how much would that shift our graph, and in which direction? Good, left 3. Remember, the h stuff is tricky, right? And it's true for all of them. You see x minus 1, whether it's an absolute value or a greatest integer function, it's shifting to the right one, not to the left one. So here, remember that this is a shift to the left 3 units, is how we would describe that translation. Okay? Oh, y equals, and it just says example, sorry. It's not lining up, so I can't fix it. So what about the absolute value function moved it up or down? The A, the H, or the K? The K. So still, again, stuff is being added or subtracted, so that's kind of our consistent thing. If it's going to fall into a translation where it's shifting stuff around on the graph, it's going to be stuff adding or subtracting. But if it's adding inside the function, we're going to move left or right, whereas if it's adding outside of the function is when we'll move up or down. So to shift vertically, you're still looking for a number that's being added or subtracted, but this time you would look for a number being added or subtracted outside of the function, like the k value in our absolute value. So the way that we write that with the special notation like we saw before, f of x would just be f of x. We wouldn't put anything new inside the function. What we would do is we would note that something was being added after the function was done. Like after the absolute value is done, then we're adding 5 to it. Something like that. Okay? So an example of that, similar to the one that was down here, if we had the absolute value of x and then we put the plus 3 after the absolute value, okay, this would now be a vertical translation instead of a horizontal translation because the plus 3 is happening outside of the absolute value bars. And what exact translation would this do? So adding 3 after the bars, what is that going to do to our graph? up 3. Okay, so we would say this is like moving up 3 units. So we'll get a little more into this later. And again, they can fall into the category of horizontal or vertical. Okay? So there can be vertical reflections, and there can be horizontal reflections. Okay. So we've seen a reflection when you guys did the little absolute value investigation on the calculator. Okay. You saw the V, it originally opened up, and then you saw one of them change so that the V went downward. What caused that change? The negative or positive A. And A, again, was a number outside of the absolute value bars. Okay? So when this number was negative, you saw it change from going upward to going downward. Okay? Would that be a vertical reflection or a horizontal reflection? Vertical, because it was open up, now it's open down. That's a vertical change. Okay? But it's kind of weird. No, it flips over the horizontal axis, but it still is a vertical reflection because it goes from up to down. So that's one thing we have to get used to. So a reflection is kind of like a flip. Okay? If it's in the category, then it's going from like up to down. Okay, so open upward to open downward. But James is right, because some of the language you're going to see with that is a little confusing, because what am I flipping over on my graph to change it from up to down? Which axis on my graph would I flip over? The x-axis, which people think like, well, x is horizontal, so that, no, it's still going from up to down. That's a vertical change, but you have to flip over a horizontal line to make that vertical change happen. So you will sometimes see the language like over the x-axis associated with this. Don't let the letter x in the axis change your mind. If you have to, pause for a minute and think, if this is the x-axis and I'm going from one side of it to the other, is that a vertical or is that a horizontal change? Okay? And again, how we see that, the A was negative. A is on the outside of the absolute value bars. So how you know something is a vertical reflection is you have whatever it is, absolute value bars, all this stuff, and you have something negative multiplying in front of it. Okay? Or, for example, in a parabola, if it had a negative 2 out here as like the A value, because it's negative, out in front of this part that's being squared, that's outside of the squaring, which makes it vertical. Because it's multiplying by a negative, that makes it a reflection. So that would be a vertical reflection. Okay. So multiplying by negatives causes reflections. Okay. What do you think is going to cause a horizontal reflection or flip, which means it goes kind of from left to right? So the stuff that was on the left side ends up on the right side, okay, vice versa. Where did we see the horizontal stuff happen before? Look back at what we wrote down about translations. For it to be a horizontal translation, stuff was still added and subtracted, just like the vertical ones, but where was the stuff added or subtracted? Inside the function for horizontal stuff. Same idea with reflections. It doesn't change what's happening. Multiplying by a negative is a reflection, okay? But if the negative is outside the function, it's vertical. Whereas if the negative is inside the function, that's going to make it a horizontal reflection. Okay? So an example of that would be maybe we have a square root function. And underneath the square root, there could be a lot happening. But one of the things that's happening there is that there's a negative multiplying with the x. That would cause a horizontal reflection.